AI is like the word on everyone's lips these days.
Yeah, it's everywhere you look.
But put them together, AI and podcast. OMG AI.
Catchy, right?
Definitely attention grabbing.
Yeah, and it tells you something about how people see AI, you know?
Definitely a sense of buckle up.
A little bit of awe, a little bit of, oh my God, what's next?
Exactly. Makes you wonder if we're ready for a podcast like OMG AI.
Maybe, maybe not.
Okay, welcome back everyone to the deep dive. It feels like we've been a bit quiet lately.
It has been a minute.
Yeah, and honestly, life's been pretty hectic. Our amazing producer, Myra, she's been, well, everywhere. Seriously, globetrotting from China to the Grand Cayman.
Wow, sounds intense.
Totally. And, you know, while she's been racking up air miles, she's had me completely buried in some fascinating projects for She Is A. They're gearing up for some really cool new program launches.
Exciting stuff.
Definitely. But it means my brain has been doing overtime, trying to process just a ton of new stuff, like really fast.
You know that feeling, that struggle to take a huge amount of, well, messy information and wrestle it into something that makes sense.
Yeah.
That's basically what our brains are built to do all the time. It's like the core job of thinking, isn't it? Turning all that sensory input, all those details into manageable, meaningful chunks.
Absolutely. Like, think about walking down the street. You see, I don't know, a robin, then maybe a pigeon. You remember seeing a hawk yesterday. Your brain doesn't log each one as this totally unique, separate thing. It just, snap, files them under bird. You compress all those specific examples, right? All the tiny differences into one abstract concept. It's like the brain's ultimate filing system.
It really is.
Yeah.
And psychologists actually have a term for it, semantic compression. We're mapping tons of different instances onto a single idea.
Right.
And the key thing, as you said, isn't just efficiency. It's not just about saving mental bandwidth. It's about keeping the meaning.
Exactly.
When you compress robin and blue jay into bird, you still know they're alive, they have feathers, they probably fly, you know, the important stuff.
You don't lose the essence and that balance, that trade-off between like squishing the data down compression and holding on to what matters, the meaning. That's fundamental to how we understand the world.
Mm-hmm.
But here's the question for today's deep dive. How do large language models, you know, LLMs, handle this exact same problem? Do they organize information into concepts like we do? Like, do they get the meaning?
Or are they just incredibly sophisticated pattern matching machines, finding statistical connections without that human-like grasp of what concepts actually mean?
That's it. That's the core question. Do LLMs strike that same kind of balance we do, that specific trade-off between compressing information efficiently and preserving the semantic meaning?
And that's precisely what the paper we're digging into today investigates. It asks if LLMs manage this compression-meaning trade-off in a way that resembles humans. The title is pretty evocative, too.
Oh, yeah.
From tokens to thoughts, how LLMs and humans trade compression for meaning.
From tokens to thoughts. Wow, yeah, that nails it. That journey from just, like, data bits to something that feels like actual understanding. And the authors are, well, a serious lineup.
They are. Chen Shani, Dan Jarabsky, Jan LeCun, and Ravid Schwartzev. A really strong team.
Definitely heavy hitters in the field.
And what I think is really smart about their approach is how they tackled it. They didn't just use AI metrics. They brought in tools from information theory.
Okay, like what?
Things like rate distortion theory and the information bottleneck principle. These are mathematical frameworks designed specifically to analyze these kinds of trade-offs, how much you compress versus how much fidelity or meaning you keep.
Interesting. So formal ways to measure that balance.
Exactly. But crucially, they didn't just stay in the theoretical realm. They grounded the whole thing by comparing the LLMs directly against results from classic human psychology studies on categorization.
Yeah.
Really foundational work.
Wow, okay. So they're using like decades of research on the human mind as the benchmark for these brand new AI models. That's a fascinating approach.
It really is, bridging those fields.
So our mission today, unpack this pretty dense paper, translate the key findings into, you know, plain English, talk about why it actually matters for how you use AI, how we all think about AI, and leave you with something to really chew on afterwards.
Sounds like a plan. Let's start with the human side. You mentioned semantic compression. How exactly does that work for us? Forming concepts.
Well, just think about the sheer number of different things you encounter every day. Every tree is unique, right? Every dog, every chair. If your brain had to store every single one as a separate item, you'd just be overloaded instantly. It wouldn't work.
Complete information overload.
Exactly. So instead, we create categories. We take, that specific Labrador over there, that poodle, that German Shepherd we saw earlier, and we map them all to the general concept, dog. It's incredibly efficient.
And that efficiency comes because you abstract away the details that aren't, well, essential for that category.
Right.
You ignore the specific wood grain of one chair, the metal folding mechanism of another, the weird ergonomic shape of your office chair, and you just collapse them into chair or maybe furniture.
But, and this is the key point you made earlier, you don't lose all the detail. You don't compress it down so much it becomes useless.
Precisely. That's the trade-off.
Yeah.
You compress, but you keep enough of the core meaning, the semantic fidelity, to make the concept actually useful.
Yeah, the concept dog still usually means animal, barks, has fur, might be a pet. You keep the functionally important stuff.
Which allows us to generalize, right?
Right.
See a new creature that fits the dog pattern, and you instantly know a whole bunch of things about it,
Right.
even if you've never seen that specific breed.
Exactly. So how do the researchers actually measure this human system, this balance?
Well, they did something really clever.
Mhm.
They didn't run new, huge human experiments. Instead, they dug up the data from really foundational psychology studies back in the 1970s.
Oh, wow. Old school.
Yeah, pioneering work by researchers like Eleanor Roche and also McCloskey and Glucksberg. And these weren't just casual online polls,
Right. These were rigorous lab studies.
Exactly. Asking people detailed questions like, okay, here's a list of items. How would you group them together? Or, very importantly, on a scale of 1 to 7, how typical or good an example is a robin for the category bird?
Typicality ratings. Like a robin feels very birdy, but maybe a penguin or an ostrich? Less so.
Precisely. That work led to what's called prototype theory, the idea that our categories aren't neat boxes with sharp edges. They're often organized around a prototype, the most typical example, with other members being more or less similar to that prototype, fuzzy boundaries.
Makes sense. And the researchers here use that original data.
They did, and this is actually a really valuable contribution in itself. They took these old but incredibly rich and rigorous human data sets, digitized them, cleaned them up, and made them publicly available.
That's huge. So now other researchers can use this, like gold standard human data, to test their own AI models.
Exactly, a real service to the community. Okay, so they've got the human benchmark measured. The next logical step, their first big research question, RQ1, was, do LLMs even create internal groupings that look anything like these human categories?
Yeah, RQ1 was basically, do LLMs naturally cluster words together in ways that match how humans group concepts? To test this, they needed to look inside the LLM.
At the embeddings.
Right. Inside an LLM, words or word parts tokens aren't just text strings. They get converted into these long lists of numbers, vectors, called embeddings.
Living in a high-dimensional space.
Exactly. And the idea is that words the LLM learned are related either because they appear in similar contexts in the training data or have similar meanings. Well, their embeddings should end up close together in that mathematical space. It's like the LLM's internal map of meaning.
Okay.
So the researchers took the embeddings for all the words from those human psychology data sets, words like robin, chair, apple, furniture.
All the items and category names.
Yep. And then they used a standard machine learning technique called k-means clustering. You can kind of think of it like telling an algorithm to find natural groupings or clouds of points in that embedding space, draw circles around the points that are closest together.
And they told it how many circles or clusters to find.
Exactly. They set the number of clusters to be the same as the number of categories defined by the humans in the original studies.
Okay, makes sense. So they generate the LLM's clusters based purely on the embedding geometry, and then they just compare. Do these machine-generated clusters line up with the human-defined categories?
That was the test. And the finding for RQ1 was pretty clear.
Which was?
A definite yes, mostly. LLMs do form broad conceptual categories that align surprisingly well with human categories. The groupings that just fell out of the statistics of the embedding space matched the meaningful human groupings way better than you'd expect by random chance.
Okay, so that's interesting. At a high level, the big picture groupings, LLMs, seem to capture something similar to the human semantic structure. Things that belong together generally end up together in the embedding space too.
Right. It suggests they're capturing some fundamental aspect of semantic organization. Was there anything particularly surprising within that finding?
Yeah, actually, they tested a whole range of LLMs, different sizes, different architectures. And while, generally bigger, newer models did well, some of the, let's say, smaller or older models Specifically, certain types of BERT models, I think BERT large uncased was one they mentioned, showed really strong alignment on these broad categories.
Huh. BERT large. That's not exactly tiny, but it's not one of the giant GPT-style models either.
Right. And in some cases, these BERT models perform just as well as, or maybe even a tiny bit better than, much larger models on this specific task of broad categorization.
Wow. So it's not purely about scale then. It's not just bigger is always better for capturing conceptual structure.
It suggests that maybe the model's architecture, or perhaps its specific training objective, BERT, is really good at understanding words and context, might play a really significant role in how well it learns these large-scale semantic relationships.
Interesting. It hints that just throwing more parameters at the problem isn't the only factor in building like a good internal semantic map.
Yeah, quality representation might matter as much as quantity. Okay, so LLMs seem to get the big picture groupings right, but human concepts, as we said, have that internal nuance, the typicality thing.
Right. Not all birds are equally birdie in our minds.
Exactly. So does the LLM capture that finer-grained structure, that gradient of typicality within a category? That was RQ2.
Yep, RQ2. Do LLMs represent the internal structure of concepts in a way that mirrors human typicality judgments? If humans think robin is a super typical bird and bat is, well, not even a bird, but let's say chicken is a less typical bird, is robin somehow represented as more central or closer to the bird concept inside the LLM's embedding space than chicken is?
And how do they measure that kind of nuance within the LLM space?
Okay, so they went back to those human typicality ratings from the 70s studies. For every item like robin and its category, like bird, they had a number representing how typical humans thought it was.
Got it. The human ground truth.
Then they tried to find an equivalent measure within the LLM. They calculated the similarity technically, cosine similarity, which measures the angle between vectors between the embedding of the item itself, like the robin vector,
Okay.
and the embedding of the category's name, the actual word bird.
Okay. So the idea is, if the LLM thinks like us, then items humans rate as very typical should have embeddings that point in a very similar direction to the embedding of the category label itself. High similarity for typical items.
That was exactly the hypothesis. So they calculated this LLM similarity score for every item category pair, and then they checked the correlation. Do the LLM similarity scores line up with the human typicality scores?
And the result, finding number 2.
Well, this is where things start to diverge quite a bit. The correlation they found was generally pretty modest, often weak. And for quite a few models and data sets, it wasn't even statistically significant. So the key finding for RQ2 is LLMs do not consistently represent typicality in the same way humans do.
So items that humans see as highly typical, like our robin example, their embeddings aren't reliably closer or more aligned with the embedding for the word bird than less typical examples are.
That's what the data suggests. The LLM might cluster all the bird-related words together effectively, but the internal arrangement of that cluster, especially relative to the explicit category label bird, doesn't seem to strongly reflect our human sense of which examples are core prototypes and which are more peripheral.
So the grouping is there, but the internal structure, the shape of the concept around its label, seems different.
Yeah, that's the interpretation. It suggests that the LLM's concepts might be more like statistically defined bags of related words. They group together because they co-occur or share statistical features in the training data.
But they don't necessarily have that rich prototype structure centered around the meaning of the label, like our human concepts seem to.
Exactly. Our concept of bird is strongly tied to the typical examples, the robins and sparrows. The LLM's bird cluster might just be a statistically convenient grouping without that strong prototype center, at least not in relation to the explicit word bird.
This is really painting a picture of potentially 2 quite different ways of organizing information. One driven by statistical co-occurrence, the other by something more prototype-based and perhaps meaning-driven.
Right. Which leads directly to the biggest question,
Yes.
RQ3. How do humans and LLMs compare in their overall strategy for balancing that compression versus meaning trade-off?
Yeah, the fundamental approach. Are they optimizing for the same thing? How efficient are they, relatively speaking? This is where that information theory stuff comes back in, right? The L objective function.
Exactly. RQ3 is all about comparing the overall strategy using this L function.
Yeah.
Can you maybe give us the simple version of what that L function measures?
Sure. So again, you're drawing those circles, the clusters. The L function basically scores how good your clustering is based on 2 things added together.
Okay.
First is complexity. Think of this as how much information you need to describe the clusters themselves, maybe how many clusters there are, or how spread out they are. Fewer, tighter clusters mean lower complexity, more compression.
Got it. Efficiency.
Second is distortion. This measures how much information you lose about the individual points inside each cluster, like how far, on average, is each point from the center of its circle. Less distortion means you've preserved more of the original detail, more fidelity.
Complexity plus distortion. And a lower L score means?
A lower L score means you've achieved a more statistically optimal balance, according to this mathematical definition. You've managed to compress the data well, low complexity, without losing too much information, low distortion. It's statistically efficient.
Okay, lower L is statistically better on this measure. So they calculate L for the human category structures and for the LLM clusters. What did they find, finding number 3?
This was probably the most striking finding. Key finding 3. Across the board, the LLM-derived clusters consistently achieve significantly lower L values than the human conceptual categories.
Lower, so the LLMs were more optimal.
By this specific statistical measure, yes. They were better at balancing compression and minimizing distortion according to the L function. And related to that, they also found that human concepts had higher cluster entropy.
Higher entropy.
Meaning
Wow.
the human categories were less statistically compact. The items within a human category were, on average, more diverse, more spread out, kind of messy, from a purely statistical point of view compared to the tidier LLM clusters.
Wow. Okay, so LLMs are like hyper-efficient statistical organizers based on this L measure. They create these really neat, compact conceptual boxes.
That's the interpretation. They seem to be aggressively optimized for statistical compactness, which makes sense, right? Their whole training is about predicting the next word, finding the most efficient statistical patterns in massive amounts of language data. That process naturally pushes them towards minimizing redundancy, creating statistically clean representations.
And humans, therefore, are less optimal, less efficient.
Well, yes. By this specific mathematical measure of statistical tidiness, our human concepts are demonstrably less statistically compact and therefore less optimal if the only goal is minimizing the L value.
But that sounds like a bad thing.
But the paper argues this isn't a flaw in human cognition. It's likely a crucial feature. Humans aren't optimized just for statistical neatness based on text patterns.
We're optimized for other things.
Exactly. We're optimized for navigating a messy, complex, real world. We need to generalize adaptively, often from very few examples. We need to make flexible inferences, not just pattern matching, but figuring out cause and effect, function, purpose, how to use things.
Right, like figuring out you can use a rock as a hammer even if it's not statistically similar to the word hammer.
Precisely. We need concepts that work for communication with other humans who might have slightly different conceptual boundaries. And crucially, our concepts are deeply grounded in rich, multimodal, real-world experience, sight, sound, touch, action, not just statistical patterns in text.
So all those other demands, adaptability, inference, communication, grounding, they push our concepts to be richer, maybe fuzzier, more flexible.
Even if it makes them look statistically messier or less optimal according to the L function. My concept of chair isn't just derived from text about chairs. It's tied to the physical act of sitting, to memories of furniture stores, to notions of balance and design and social function.
That makes it incredibly powerful for dealing with novelty, like figuring out a tree stump can be a chair, or understanding the chair of a committee, things that might break a purely statistical model.
Exactly. Human concepts seem functionally optimal for thriving in our complex world, even if they sacrifice some statistical tidiness. LLMs are statistically optimal for modeling language patterns. They're kind of playing different games, optimized for different goals.
Okay, this is really clarifying. So let's pull this all together. What does this mean for us right now? Why should someone listening care about this difference in optimization? What's the impact? Does it change how we should be using AI today?
I think it's fundamental. This core difference, LLMs driving towards statistical compactness, humans towards adaptive richness and functional utility, is absolutely key to understanding AI's current power and its limitations.
Because LLMs are incredibly powerful.
Absolutely. Their mastery of statistical patterns allows them to generate fluent text, translate, summarize, answer questions in ways that often feel remarkably intelligent. They can mimic understanding very convincingly.
The engine underneath is different. The way their concepts are structured isn't built on the same foundation as ours.
Exactly. Their internal representations are optimized for that statistical tidiness we talked about, not necessarily for the deep, flexible, prototype-based, grounded understanding that humans develop through experience and interaction with the world.
So what does that mean for you, the user?
It means you need to be aware that this difference exists. It helps explain why LLMs, even the best ones, can sometimes feel brittle. Why they might generate text that sounds plausible but misses a crucial nuance, or makes a weird, unexpected error when faced with a situation slightly outside the patterns they've learned extremely well.
They lack that deep, flexible, conceptual grounding that lets us handle ambiguity and novelty so naturally.
Precisely. So, should it change how we work with AI now? I think yes. It reinforces that LLMs are phenomenal tools for tasks that rely heavily on recognizing and manipulating statistical patterns in language writing drafts, summarizing information, coding assistance, translation, but relying on them for tasks requiring deep, context-sensitive reasoning, genuine common sense, or truly adaptive generalization to novel situations. That requires caution. We need to understand their strengths are in pattern processing, and their understanding is structurally different from ours. Be aware of the potential for subtle failures in nuance and flexibility.
And looking forward, for the future of AI, this research seems to suggest just making models bigger and training them on more data might not be enough.
It strongly implies that, doesn't it?
Yeah.
If the goal is more human-like understanding, robustness, and adaptability, simply scaling up the current paradigm of optimizing for statistical prediction might hit a wall. We might need different approaches.
Like what?
Well, the paper doesn't prescribe solutions, but it points towards needing to explore ways to build models that develop richer, more nuanced conceptual structures. Maybe through different training objectives that explicitly reward generalization or grounding in other data types beyond text. Maybe new architectures entirely.
And the framework they develop, the L function and comparing to human data?
That gives us a tool. It provides a concrete, quantitative way to start measuring whether new approaches are actually moving towards models that find a different, perhaps more human-like balance between compression and meaningful representation.
Okay, so let's try and wrap this up. The big takeaway seems to be, LLMs are masters of statistical compression. They form broad categories like us, but the internal structure, the nuance like typicality, isn't consistently human-like. Their core drive is statistical efficiency.
While humans, using the same measure, look less statistically optimal. But that's because our conceptual system is optimized for different, arguably harder things. Adapting to a complex world, making flexible inferences, grounding meaning and experience, we prioritize functional richness over statistical tidiness.
And knowing that fundamental difference helps us understand both the amazing capabilities and the current limitations of AI.
Absolutely. It's a different kind of intelligence.
Which leaves us with a really provocative thought to end on, something the paper implicitly raises. Our human way of thinking, which looks suboptimal or messy if you only measure statistical compression. Maybe that's the secret sauce.
Could it be? Could that apparent human inefficiency, that tolerance for higher entropy or fuzziness within our concepts, be precisely what enables our incredible flexibility, our deep understanding, our ability to generalize and create?
It's a fascinating question. To get AI to move beyond just processing tokens towards something more like genuine thoughts, might we need to figure out how to build systems that don't just optimize for pure statistical compression?
Systems that perhaps value rich nuance, adaptability, maybe even embrace a bit of measured statistical inefficiency in service of those higher goals. This research gives us a framework and a benchmark to start asking and testing those kinds of questions.
It really does. And for anyone listening who wants to dive even deeper into the data, remember the researchers made that combined human data set from those classic psychology studies publicly available.
A fantastic resource for the community.
Absolutely. Well, this has been a fascinating deep dive. Honestly, it puts a lot of the work I've been doing with Xiaoziel into a new perspective. It's a crucial reminder that just because an AI's output looks smart, the process underneath might be operating on very different principles than our own minds.
A vital distinction to always keep in mind.
Indeed. All right, that's our time for this deep dive. Thanks for joining us, and we'll be back soon to explore something completely different.